Hey, it's Mr. K doing a problem revisit. I've got the Grasshopper problem here. And I was working this problem today and I realized that it's a much more elegant problem than I first thought. And that's due to symmetry. So if you have been working this problem and having a really hard time with it, just don't know where to go, exhausted all of the equations and all that other stuff, just still don't know where to go, well, here's a little bit of help with that. So the problem starts off saying that you have a grasshopper and it jumps a distance x, and it gives you this number in the problem. So let's say that the number is like 0.8 meters. And it tells you that the grasshopper jumps at a 45-degree angle. And so if that grasshopper jumps at a 45-degree angle, we have some initial velocity v naught here. It does not tell you what it is, but it does say that, hey, it jumps in the air, it lands on the ground, and it goes 0.8 meters or whatever your number would be. And it says, hey, what is the velocity in the x direction, the horizontal velocity for this grasshopper? And so, a lot of you will be looking at this thinking, I just don't have enough information. And it might seem that way at first, but whenever that's the case, you always try to work from your equations. And we have these equations, like this first one says, hey, the final velocity after some acceleration happens for a time, we tack that onto the initial velocity, and we're going to tell how fast we're going to be moving after that. Or this equation says, well, maybe we don't have time, but we definitely have initial and final velocities, and we're going to multiply the acceleration by our change in position and by 2, and there's a derivation for this. I'm just giving you this equation, but it has a lot more to do with energy. So this might be useful if you don't have time. Or this one, which says, hey, we go so far, depending upon how fast we're initially moving, for a time, and we're going to add 1/2 a t squared to it. And this equation actually comes from just looking at how things move with or without acceleration, and it's really from graphing. So you've got these three equations, and if you're totally stuck, then you write out your list of variables, and we've got initial velocity, final velocity, acceleration, the change in time, the change in position x, the change in position y. And you just say, all right, well, how many dimensions are we moving in? Well, we're jumping up and over, so we're moving in 2 dimensions. And we really don't know a whole lot about this, except for the angle is 45 degrees, and that's going to become very, very useful to us. And so the realizations that you need to make here are that you don't have a whole lot, but you can start to put things in. Like, we know the acceleration due to gravity, negative 9.8 or 10, I'm just going to put negative g there. We know that in the horizontal there is no acceleration, there is no force sideways. This is from a force downwards from the pull of the Earth. We know that it starts here and ends over there, which means I know the change in x. I know that that's going to be 0.8 meters. I know that I start on the ground and I end on the ground. And so I can say, all right, well, we definitely know this. The delta y, the change in position y, is nothing. And if we knew the horizontal velocity, then we would know that it wouldn't change. If we knew the vertical velocity, well, one thing we know is that if we jump and come back down, on the way up, gravity is slowing us down, and on the way down, gravity is speeding us back up. And so whatever the velocity is here in the y direction initially would be the same velocity here. Well, initially, it would be the same velocity in the y direction in the end, except that it would just be negative, because gravity slowed you down on the way up, it sped you up on the way down, and it was for the same amount. This is your parabolic arc. And velocity in the x direction, we don't necessarily know what it is, but we can just say vx. And if you wanted to get more complicated, you could say, all right, well, the velocity in the x direction would be the horizontal piece of this diagonal. And you might say that the horizontal velocity would be the initial velocity times cosine of the angle. Or the vertical velocity would be the initial velocity times the sine of the angle. But this problem is really kind of pretty in the fact that it's 45 degrees. And what we know about 45 degrees is that it makes for a very nice square if you were to continue that out, or at least, this right triangle with two sides that are the same. And so we're gonna kind of work with that concept. And so what I have here is that the initial velocity, whatever it is the same in the horizontal and in the vertical. And I'm really looking for this. I'm really looking for the velocity in the x direction. So that's my end goal. And if I want to find it, well, I know that velocity is It's a change in position over the change in time. We're talking about one dimension, so it's a change of x position over the change in time. And well, we know how far we are in the x, so really all I got to find is time, and then we'll be good. So that's pretty much what I have in the x column. But in the y column, if I can only find time, then I'll definitely have somewhere to go and find that change of x if I wanted it. So I'm looking over here, and I have two equations that have time in it. This bottom one's a little bit more difficult. We don't really know. Actually, well, we could solve for it, but we really don't know what the vertical velocity is. But again, the cool part about this problem, if you want to call it cool, is that the horizontal stuff and the vertical velocity is the same in the beginning. So really, this velocity, I could just as easily call it Vx in the beginning. I could just as well call this negative Vx in the beginning because of that 45-degree angle. And if I go back and I talk about what acceleration is like a change in velocity over a change in time. And that's basically the first equation. That's how you get the first equation, is from this definition. My change in velocity, I start from positive Vx to negative Vx. And so my change in velocity is twice Vx. Positive Vx to negative Vx, it's twice Vx. And that takes some period of time to do it. Okay? And it's a negative change. And so that acceleration, again, is going to be from g. I'm just going to say it's negative g, negative 9.8. And those negatives will cancel out. And I can solve this for time by just multiplying and dividing, multiply by t divided by g. So 2Vx divided by g is equal to the change in time. And that is super useful. And so this equation, this problem just became very elegant, I feel like, because we can just take this time and plug it in here. So the velocity in the x direction is equal to this known position change x divided by 2 times the velocity in the x direction, because it was all symmetrical, and we can divide that by g. And if you divide the denominator by anything, that something pops up to the top of the equation. So I have the change in x times g divided by 2Vx is equal to Vx, which you're not stuck here, really. All you got to do is move the Vx over, and that would give you Vx squared. Multiply both sides by Vx squared. And this equals the change in position x times g divided by 2. And your final answer is simply this, because you're looking for the horizontal velocity. It's the square root of how far you go times your acceleration due to gravity divided by 2, and that's your answer. Make sure everything is under the square root. And so initially the problem looks like it's going to be really difficult, but really it's actually not. And it becomes very, very simple once you realize some basics of it, which are just using the symmetry. So hope that helps, and have a good night.